Good evening. I'll be presenting the hydraulic flood modeling using the HEC-RAS software on one-dimensional scenario for the Pongola River. This is the project assessment. On the introduction, South Africa is faced with an increasing flood risk due to the climate change and the development pressure. And then the Pongola River catchment is vulnerable despite the upstream regulation by the Pongola Port Dam, and the production tools like the hydraulic modeling are essential for the integrated flood risk management. The flow behavior in the natural river system. The river flow is a natural system shaped by geomorphology, sediment transport, and vegetation. And then the Pongola braided channel and the floodplains causes complex variable flow path. The small variation in slope and the catchment width or the vegetation impact depth and energy loss, the agricultural encroachment and invasive species, the supercritical flows may occur locally during the extreme event, and the transition like the hydraulic jump are often oversimplified in local modeling. And then the flow modeling, the following will be looked at: the role and importance, the modeling category, focus on the one-dimensional model of flow, sustainability for the river, that is the Pongola River, the limitation of the 1D modeling. Then now, if you look at the role and importance, the hydraulic modeling is critical for prediction of flood in river and floodplain systems, and the supposed disaster risk reduction, the spatial planning, and infrastructure designs. That's the importance and the role of the flood modeling. And then the categories of modeling: there is the hydraulic model, and which you look at the simulation on the rainfall and runoff processes. And then secondly, the stimulate on how water moves from a river to floodplains. And then the focus on the one-dimensional. The one-dimensional model simulates flow along the river, and it's ideal for steady flood analysis. And thirdly, the efficiency and the interpretable by non-specialist stakeholders. And then fourthly, the sustainability for the Pongola River. One, the data scarcity and the relative simple river structure makes 1D models a practical choice to simulate. Two, it enables a simulation of water surface profiles, energy gradients, and overtopping locations. And thirdly, it's used for regulation and floodplain mapping and the scenario planning in South Africa. And then lastly, the limitation of the 1D model: it cannot simulate lateral or multi-directional flow, and again, it may overestimate the extent in the complex of the terrain. And now, if you look at the steady and the unsteady flow modeling comparison, the steady flow modeling, it assumes a flow at each location remains a constant overflow. Two, it uses for determination of peak water surface elevation under design discharge. And then thirdly, it applies for infrastructure designs, that is on the dam safety, regulation of floodplains. It is ideal when timing of flood wave is not critical. And then it's easy to set up with the fewer inputs in the data requirements, and the steady model preferred due to data scarcity and limited time real-time monitoring. And then lastly, they are appropriate for assessing worst-case flood levels in scenarios-based analysis. And now, if we look at the unsteady flow model, it captures flow variation over time. It stimulates timing of wave arrival velocity transitions, and then it requires hydrograph time series information or data, and it's more complex calibration. And again, it's also more realistic but demanding in terms of information or data that is required. And the unsteady model limited by a lack of continuous discharge and records of hydrometric stations. The comparison on the key characteristics on the both steady flow and unsteady flow modeling. If you look at the main key features like the flow assumptions, the output type, computer session on load, the data requirements, primary use case, the strength, limitation, and sustainability in Pongola River. If you look at the first feature, the steady flow modeling, it discharge and the velocity constant with time. And then on the unsteady flow, the discharge velocity and depth vary with time. And then on the second feature there, water surface profiles at peak discharge. And then if you look at the unsteady, the time series of discharge velocity and time series of stage velocity and discharge. The third feature on the low to moderate, and then the unsteady is quite high, and steady matches. And then the fourth feature, the minimum, especially on the design flow, the channel, the geometric roughness. And then if we look at the unsteady, the extensive, that is on the continuous hydrographs, the terrain information data, the rating depths, and so forth. So all of this information it differs on each and every feature that is used between the steady flow and the unsteady flow. And then the methodology for this assignment, the focus was on the steady area. The study area is about 6.25 kilometer reach of the river, the Pongola River, and then it stretches between or into 25 cross sections that are spaced roughly about 250 meters. Then the geometric data preparation, that is the cross section, and the geometric provided and other information that is generated. And then there was the adjustment made to width and the elevation to reflect the real world. And lastly, left to right overbank stations are assigned during the proportional scaling from time-based section. Then if you look at the data source and the approach, no high resolution in terms of the survey information, and the approach ensures that the topographic, continuous, and the floodplain represent across the ridge. And lastly, on the model itself, the model integrity, it's the geometric validity to ensure the hydraulic consistency and to avoid the geometric anomalies. And lastly, ready for input into the HEC-RAS software for steady flow simulation. That is the methodology of the assignment. Then if you look at the steady flow simulation in river, of which this part is also detailed in the report, the hydraulic modeling framework, which simulates the based on uh, gradual variation steady flow. And then in terms of the equation that's been used for the total energy, where the Z is the bed elevation, Y is the depth, the velocity, and the gravity. And then all of these obviously will be solved in HEC-RAS between each pair on the cross sections. And then the friction losses and the main equation, this is the main equation that's been used, including the geometric transition losses. And then in terms of the model setup of the HEC-RAS software, the following in terms of the software enriched definition, this is a software that's been used, and then it's simulating the Pongola river, and then the cross section built using geometric generated information from the Excel, which is I've also attached on the report. And then if you look at the flow scenarios, the flow scenario is based on the 2,500 cubic meters, and then the design flood is a 1:50, and also 1:100. That is the scenario for the flow. And in the boundary conditions, I've looked at the upstream and also the downstream on the normal depth of the riverbed slope. And then on the energy losses, the coefficients applied to account for change in the cross sections. These are the figures that's been used, and then the model output. The model output will focus on the water surface, the energy grade line, the float number, and also the flow distribution between the main channels and the overbanks. And on the results, after the software has been used, based on the cross sections and elevations of the water surface profile, bed elevation, and then this is the output from cross section 1 to cross section 25. And then in terms of the total rise, there's about 43.6 meters over. And then in terms of it also indicates a steep slope profile on the bed elevation trends. And then the water surface profile based on the 2,500 cubic meters per second. And then in terms of the effects of geometry, the cross section, it's between 6 and 8, that's a plus 2 to 4% in terms of the width and the elevation. And then the cross sections between 12 and 11 and 12, these are the figures. And then in terms of the interpretation, the results aligned with the principle of gradually it varies. And then the backflow effects profile from M1 profile, it also included in the report. And then these are some of the outputs that came from the software. And then in terms of the results on the float number and the flow distribution, the float number analysis, the float number remains below 10, and then it also ranges between 0.4 and 0.8 consistently with the gently slope. Then in terms of the zone elevated velocity, the cross section that is 8 to 12 shows a higher float values. And then it also indicates a higher energy zone with the potential for localized instability under flat conditions. And number 4, in terms of the results, the flow distribution across the channel. The main channel carries most of the flow, that is in cross section 1 to 10, and then the overbank zone, increase in elevation and reduce channel capacity cause lateral spreading. Then lastly, in terms of the implications for the floodplain management, it supports prioritization of the upstream areas for interventions like the Livier constructions, the vegetation buffer zone, and the land use restriction in the banks. And then these are some of the outputs from the, and in terms of the results, the meaning roughness and sensitivity based on the following. The base scenario roughness values, the meaning and values is used is 0.015 for the main channel and the 0.025 for the overbanks. In terms of the sensitivity analysis, two alternative scenarios tested. Um, and then in terms of the effects of increased roughness, the water surface elevation increased, and then the flow velocity, that is mean velocity decrease due to the increase in boundary friction. The yield implication and risk, the field implication and risk, the field conditions like the vegetation growth, the debris, and the sediment deposition can also or increase the channel roughness. And then in terms of the reinforced, the need for regulation calibration of the meaning, which is the N value. Then these are some of the outputs, the screenshots, and then the one-dimensional simulation results from the software. And then this is the profile analysis, and then these are the results or the profile output table, also from the software. And then this is the cross-section output, the screenshot from the software. And then in terms of the running and the simulation of the different conditions, these are some of the results from the software. And mostly in terms of the recommendations, number 1, the floodplain management, cross-section 15 to 25. It prioritized the upstream flood prone zone for intervention. And then 2, the implement, that is the bank protection and the vegetation buffer. 3, enforce strict land use policies to reduce development in those floodplains. And then number 4, supported by the DI. And then number 2, the roughness calibration, field calibrated meaning N reduces the molded errors, and then also apply the Cohen method. 3, the uniform roughness doesn't capture local changes, that is in terms of the vegetation or the debris, and then the use of historic flood data. 4, in terms of the hydraulic optimization, that is between cross-section 6, 8, 12, and 11. Constrict zone below the backflow effect. In terms of the recommendations on the hydraulic, is that sediment removal, channel regrading, the moderate widening of the channel. Then in terms of the flood preparedness and early warnings, the upstream sections are overwhelmed by 50 and 100-year floods. Then in terms of the catchment scale integration, extended model to entire watershed. and then a couple HEC-RAS with rainfall runoff models and land use data sets. And then also integrate the IPCC climate projections for extreme rainfall and scenarios. In terms of the conclusion, if you look at the conclusions, there are four main conclusions in terms of this project. Number one, the model overview applied one steady state HEC-RAS on the river. The simulated subcritical flows. In terms of the key findings, the key findings on the upstream slope, there's the significantly shaped flow patterns, and then the geometric constrictions, that is in the cross section 6, 8, 12, and 11. These are caused backwater effects. Then on the energy shift to overbank zone increase, the erosion and flood, and the rising roughness by 40 to 70% in terms of elevation. And then the model value, HEC-RAS, prove an effect for geometric sensitivity flood scenarios, and it also supports planners and engineers in the development of resilience and adaptive strategies. Lastly, the implications. The existing infrastructure may be inadequate for high return flood, and the critical need for monitoring systems, early warning mechanism, and the climate change or the climate adapting flood management. And then these are some of the references used for the report or the project.